Okay, problem 10. This is actually a very interesting one because this gets into work and energy, really. Or effectively, this problem asks you to do work and energy almost without realizing it. So, 3.4 kilogram book is pushed from rest, sorry, through a distance of 0.90 meters by horizontal force of such and such newtons, and then has this final speed of this. What is the coefficient of kinetic friction between the book and the floor? So, let's see. We've got this. Let's take a look and say we've got this book here. Let's see. Let me try again. That's a little more horizontally. All right. So there's our floor. There's our book. Initially, oh, I don't want to add the colors. Stupid paint. All right. So V initial is 0, and then book's final velocity is given. So we'll just say, it has some final velocity here. Okay. So, and then it covers some distance, some distance delta x when it does. Okay. So, what we're going to do is we're going to start with, and while it's happening, it's got a force, a horizontal force from the broom, and then there's a friction force going that way. There's a normal force, and of course there's mg. What we're really being asked here is to find the magnitude of the friction force. We're given this force. We're given this applied force from the broom. We're being asked really to find the magnitude of the friction force. Getting the coefficient of friction just means doing, the normal force and all, and that's fairly easy. What we're really being asked to do here is find the magnitude of friction force. So, obviously these forces are going to cause some kind of acceleration. I mean, if it starts at rest and then at the end it's moved some distance, it can't just, sit there and move. So obviously it must be accelerated by this force. So there's your acceleration. So let's go ahead and recall one of our equations from two-dimensional motions, which is v final squared equals v initial squared plus 2 times acceleration times delta x, so how far you travel. So what's interesting about this is, and you're going to have to sort of take this on faith here for a second, but if you look at what's happening here, if you multiply both sides by m, v final squared equals m v naught squared plus 2 ma, for parentheses around that, times delta x. This in here is actually the net force on the object, right? So ma is the net force on the object. So I'm going to do, stopping right there for a second, so just hold this thought. I'm going to draw a free body diagram of the book. Okay, so this is our x and y. Okay, so x and y. Here are our forces on the book. Normal force, mg, the applied force from the broom, F, and then the friction force. Now, if we do all of our sum of forces in y, it's not going up or down. So sum of forces in y is 0. Normal force, therefore, since it's normal minus mg, mg equals 0. Normal force equals mg, which means force of friction equals mu k times n equals mu k times mg. But you know what? I'm going to hold off right there and not do that yet. So let's remember this. I'll do the baby blue as sort of our little, remind us of that later. But remember that. But for now, we're just going to move on. Sum of forces in the x direction is so it's accelerating to the right, positive x. So this is going to equal mass times acceleration. And the sum of forces, well, what forces do we have? We have F going to the right, and we have the friction force going to the left. Those equal ma. Okay, so what this says is the net force in the x direction. The net force in the x direction is, the sum of the forces in the x direction. That's positive F, negative friction force. Sum of forces in the x direction equals ma. This is just Newton's second law. Newton's second. Okay? That's where this comes from. Hang on. There we go. Let's not cover our F. Okay, so we take this equals ma, plug it in up here. So there's our ma, there's an ma. And we're going to take this down here. And we are going to say m v final squared equals m v initial squared plus 2 times, how do I want to do this? Let's see. So I'm just gonna change. So I'll tell you what, Newton's second law is net force equals ma. Okay, this is our net force, but I'm just going to do it this way for a second, so I can have F net, okay, times delta x. So here, now keep in mind, this is not, we haven't done anything specific to the book yet. We're still keeping v naught squared, v final squared, mass, delta x, and F all symbolic. So this is all just still symbolic for any kind of one-dimensional motion. Now what I want to do with this, to take it just one step forward, is I'm going to multiply this by 1/2. This, where you are right now, this kind of feels like something I pulled out of my ass. Okay, and in a sense it is. I mean, I just sort of know the answer here, and I know that if you do 1/2, multiply everything by 1/2, then it cancels this 2, right? So we got the 1/2s here, but then we cancel this 2, plus F net times delta x. Now, believe it or not, this is something we're going to be discussing sometime. I'm not sure if it'll be before Christmas or after Christmas, but this is kinetic energy. It's the energy of motion. Kinetic energy, final kinetic energy, because we v final. 1/2 mv squared is kinetic energy. And this is the initial kinetic energy. So that's this term here is final kinetic energy, 1/2 m v final squared. 1/2 m v 0 squared is initial kinetic energy. There we go. And this is the work done on the book. Work is basically the product of force times distance. If a force acts on something as it travels through a distance and they're both in the same direction, this is it. If they're in different directions, we have to do things with dot products. But because it's all one-dimensional here, this is it. So kinetic energy equals 1/2 mv squared, and work equals F net times delta x. And this is one dimension. Okay, so what this is just final kinetic energy, initial kinetic energy, work. Now if you look at the change in kinetic energy, is 1/2 is this minus this. So change in kinetic energy, okay, is let me do this a little, Ke final minus Ke initial, or actually I'll do that, okay, minus Ke initial. Okay, so this is just change in kinetic energy is Ke final minus Ke initial, and that's going to equal 1/2 mv final squared minus 1/2 mv initial squared. So that's just taking this and pulling this over here. Okay, change in kinetic energy is work done. And work, as I said here, is net force times change times distance traveled next. These are all scalar quantities, and this is a way you can, this will be useful later on when we're trying to short circuit stuff. We're trying to do, basically it's a great shortcut for many kinds of problems, and it lets us do problems that wouldn't be doable otherwise. Okay, so enough of that crap. I'm just going to take this now and actually make this just something useful algebraically with this. So 1/2 m times, let's collect our terms here, v final squared minus v initial squared, okay, equals, and our net force here, let's see, F net, which is equal to ma here, is F minus your applied force from the broom, remember, minus the friction force. So remember what we were actually talking about before I started blabbing about energy, is that we had this book being pushed by a broom to the right with a friction force to the left pushing back. Okay, so that's what our F net is, F minus FF. So F minus force of friction times delta, actually I'm not even going to put parentheses on that, just delta x. So for this problem we were told the book started at rest. So actually it's even easier than that. Yeah. So it's 1/2 mv final squared, because this is 0, equals force minus your friction force times delta x. And so your friction force due to friction, is equal to, the way this comes out, mvf squared, oh boy, let's see. Well, actually this is going to be even worse than I thought. So let's just take this and, okay, actually let's erase all that. Okay, so then let's get our paintbrush back, and so 1/2 mvf squared, no, hang on, v, there, big F, there, okay, there we go, vf squared, make it both negative, let's see, f delta x, yeah, well, let's see, f delta x all over delta x, and this is kind of ugly, but you get the idea. Okay, equals the friction force. So that should work out, right? Yeah. Okay, so that's going to give you your friction force, and then your coefficient of kinetic friction is going to equal the friction force divided by the normal force. And if we come back up here, we did our free body diagram here, the normal force is mg. So equals friction force over mg. And so I know this is an ugly ass equation, but FF equals, let's see, no, hold on, friction force, oh right, I'm sorry, we already had a, damn, I'm not doing good right now, am I? Alright, so let's get this sort of weird brownie color. So mu k equals this friction force divided by mg, which is this. So this is F, I'm going to cancel these delta x's on this term, over mg minus, and then we have this delta x here, so m, although actually this m cancels, so it's going to be like v sub f squared over 2g delta x. So there you go. Pardon me for taking so long to get there, but that is the answer.